Hello, everyone.
Hello.
Okay, so welcome back. So first, I would like to remind you that the midterm report is due Sunday. I don't know how many of you have looked at it. Basically, this is a set of 5 questions that I would like you to answer. Basically, it's a way to reflect what you have been doing. How are you doing so far in this course? And also be a feedback for me to adjust how I perceive the later lectures. Okay. And today I'm going to talk more about topological quantum computation, and I will also review some aspect of Toric because these are useful. This is a concrete example that illustrates many useful aspects of quantum computation, but not all, but we'll see. Okay, yeah, so we're entering the week 7th subject. So first, let me just give you an overall picture of topological quantum computation. Basically, it uses some kind of topology to protect against errors. In the Toric case, we have the metaphor is on the torus, and because of the topology of the torus, there are 2 encoded qubits, and in order to cause errors, we have seen that these errors need to be expanded across the system. So that's a way to use topology to protect against errors, but we'll see other examples. And in these topological system or the intrinsic topological phases, there are strange particles called anyons. These are excitations, and we have seen some of these in the Toric case. And interestingly, they form the braid group that they form would give rise to some gate operation, as we will also see today. Then when you measure, you probably want to annihilate that into the vacuum, and then you can read out the outcome. Okay, so I would review Toric some examples. So we have qubit on edges, and there are 2 n² edges. So this is using 2 n² qubit to encode 2 logical qubits, and the code distance is n. So that means that it can correct errors n-1/2. So that is a really large code distance, because in order to really make error, you need to have corrupt half of the side along one direction. And assuming that the error rate is low, that is not going to be happening. And we see that in this Toric, the Hamiltonian we consider are sum of 2 kinds of stabilizer. One is the so-called star operator, which is product of sigma x or x around a vertex. The other is the so-called plaquette operator. It's product of sigma z or z's around a plaquette. Yeah, and this is the stabilizer group. And we can also see that in the ground state, basically AS and BP, it's a number, it's 1. If you act on this on the ground state, it should return to self. So you can basically regard this as 1. And therefore the excitation will be making some of these A's and B's to become a -1. And we know there are constraints of these operators. So product of all the star operator become identities, so the excitation comes in pair. So as illustrated, if I apply a Z operator, let me make this a little bigger. If I apply a Z operator, so Z operator would make the Z operator would make the vertex, the star, become a -1 because it anti-commute with a sigma Z would make for this particular Z would make the neighboring vertex become -1. If you apply another one, you would make this one plus and this one minus. And essentially, the more Z you apply, you're dragging along these excitations. Now, this particular one, we call it charge excitations. And the other one is violation of the plaquette operator. Basically, you use X because it's anti-commuting with sigma Z. So you create two minus sign on neighboring plaquette. But if you apply one more, it will move one of the minus sign along the direction you apply the X operator. So you see that this creates a pair of M excitations. And this also shows you how you correct errors, right? So you see that if you can measure the value of these stabilizers, if you see a pair of minus sign, what you do is you try to find one of the possible paths connecting the two minus sign, and you would like to find the shortest distance. Then you apply these corresponding Z operator along this path, then you can correct errors. Unless the error occur, unlikely that it almost wrap around and you actually using the path that form together with the error that form a big circle, then that would actually make a logical operation on your code space. Okay, but assuming the error rate is low, it's probably always a good idea to find the shortest path connecting to. And actually, it doesn't matter how you connect them, right? You could also find this path here. And there, in addition to the charge excitation and flux excitation, there is another kind of excitation that is consisting of a bound pair, E and M. So as illustrated here, this is an E, this is an M. If you sort of try to make them bound together and move together, these form fermionic excitations. Okay.
I have a quick question.
Yes.
So this EM excitation, how do you create them?
Yeah, so as I said, so if you start with vacuum, right? You start with this ground state. I apply a Z operator. That's frustrated is that created -1 and -1, right?
No, so the EM, the combination fermion.
So you can apply, you can apply another X.
Oh, right? Okay, it's just Z and X.
So this would be like that, right? As indicated, as indicated on this. Yeah.
Okay, thank you.
Okay, sure. So that's why it's called bound. So you want to have the X and Z, some kind of error operator, they sort of bound together. It might also be possible to apply X and Z together, but the direction might be slightly different. The Z would create here and X would be the opposite. Okay, but these are minor detail, but because if you look away from distance, if you have sort of pairs of string X and Z, they should form pair of fermion. Okay, so we have seen that there are 4 types of anyon. Vacuum is the trivial one, charge, flux, and fermion. And it turns out that E or M themselves, they are boson, so that when they exchange E exchange among E, the wave function give a plus sign. But the fermion, if you exchange, you get a minus sign. Yeah, sorry. This part is for the. If you loop around E around M, you have a minus sign. So they are the so-called mutual semyon because you loop around, you get a minus sign, and that gives you sort of half of the. If you take square root of that, that's sort of half of a fermion. That's called mutual semyon. And for fermion, if you loop 2 fermion together, you cannot actually find a minus sign, right? Because 2 exchanges give you a plus sign. So in some sense, the rotation E around M, so this is F, is plus sign. Say take this E and loop around, it's a minus sign. So in some sense, not quite rigorous. If I sort of exchange E and M, it's sort of half of that, right? Half of this face, so it looks like an eye, so that's half. So that's why I call semyon, but they are relative, E and M. Okay, but that's just minor detail. Okay, so then we talk about the ground state, how we get the ground state. And to write down the ground state explicitly, you first take all the qubits to be in the 0 state. This certainly will satisfy the pocket operator, but does not satisfy the star operator. However, star operator flip for 0 to for 1, or if you have this, it would flip to 1, 0, 0, 1, etc. So the idea is that given that we satisfy BP, now we try to satisfy AS. The idea is simple, you just sum all possible flip. Right, therefore, any AS is part of that, so it gets absorbed into the G here. Okay, so that's the idea. And because BP commute with AS, so application of BP on the ground state will still be giving you a plus sign because BP applied to that. It commute with all these AS operators, but this is plus sign. So it returns the ground state itself. Okay. So a pictorial way to understand that is the ground state I label as 0, 0 is an equal superposition of all possible contractible loop. I think it's illustrated here. So one example of a loop is the edges crossed by these dashed line have 1. All the rest are 0. So let me just write 0 everywhere else. These are local loops, right? They're contractible. And the ground state is sum of all possible configuration you can think of, like this. And that's the ground state, one of the ground state, because we know there are 2 qubits So how do we find the other 3 ground state? So the idea is using the logical operator. So given that this would be our logical 0, 0 state, right? So if we have 2 qubits, we will write as 0, 0. So then we use the stabilizer formalism to find operator that commute with the stabilizer, all the stabilizer operator, but not in the set. And you want to find 2 set of them, x1, z1 for qubit 1 and x2, z2 for qubit 2. The requirement is that these have to commute with the stabilizer group. So meaning that the action of stabilizer group, any of the action of stabilizer group on the vacuum, so this is the same, right? So meaning that if you get a ground state and you try to apply these pocket operator or star operator or any combination of them, you still get the same state. Essentially, there's no effect, okay? But these logical operator, they are product of X. This example, product of Z. They are in non-trivial big size circles. So the effect will not be trivial, as we'll see. And let me just describe these logical operators. So the first, I define the first logical X is along this vertical direction, and the logical X operator for qubit 2 is the horizontal direction. And you might see that why I have the logical Z operator parallel to the logical X2 operator. The reason is they don't have any edges that cross, right? That means they would commute, right? These two would commute because they don't have any shared edges, okay? So that defines the 4 logical operator. And we see that x1 is the vertical X here, and the horizontal Z1, they cross here. So they have a one location that cross. That means X and Z will be minus. So X and Z would intercommute. That's why there's a minus sign, and that satisfies the logical property of these operator. Okay, so from the 0, 0 ground state, you can flip to other ground state. I should write here, right? So basically, the G01 state is basically X1 applied to Z00, or the other way around. 1, 0. Okay, 0, 1 is X2 applied to this. So basically, the 0, 1 subscript 1, 1, 0, 0, 0. These representing sort of labeling of logical qubit. G11 is X1, X2. Okay, once you are at the logical level, you can forget about the underlying physical way of getting these operators. So you can really just treat them as a logical. Okay, and the pictorial way of understanding these other ground states are as follows. You use the 0, 0 ground state as your starting point. For example, you apply x2, which we define in the horizontal direction. You apply these x indicated here. That flip 0 to 1, so there is 1 here and 1 here, 1. And this was a 1 here to get flipped to 0. So therefore the loop is become a non-contractible one along the horizontal direction. Okay. And you may also ask, well, maybe I could apply this one or apply that one. These would give equivalent configuration because you just apply, you can, for example, you can, this is x, right? So x. What if I apply x like this? What if I apply x like that? So like this. As opposed to the horizontal line. So you can see that this is nothing but applying a AS operator here, right? So then I remove this x and create x here and x here, x here, and that can deform. You can deform the loop. So basically, what I'm saying is that x2 is the same as a x2 times any star operator or pocket operator in any combination, right? So you may see that if I do that, this particular configuration is different, but there will be another configuration that turn into this one as well. So this because ground state is summation of all, in this case, non-trivial loop like that, and has winding number 1. So this is a topological property. Okay, so the other you can understand is the other direction. You apply x this, and if you apply both, then it would have winding number in both directions. Okay. Any questions so far? This is part of the review of last lecture's material. Yeah, so I want to talk a little bit more about anyons because in the next part, I'm going to use anyons as my starting point. So we have seen the 4 anyons. So identity, electric charge, magnetic flux, and fermions. Saying for example, this fermion is a bound state. So you can regard as if you fuse E to M to get a fermion. And therefore, you also have other property that if you fuse E to the fermion, you get back to the flux. So there are also other property. If it's a vacuum and you fuse the E, of course, it will be E. Vacuum fused with anything would just be that thing. Yeah, and also this is consistent because if I fuse E to E, it's identity. So this property basically says that E and E, like that, for really far away, this looks like a vacuum. So if you have a E and E here, really, really far away, after long distance cross graining, this looks like there's no excitation. Okay, but in terms of our error correction properties, that this can be corrected back to the vacuum. And I told you that F is a fermion. However, a rotation of E and M has a pair around the other one. Even for fermion, it's a plus sign. So how do I see this minus sign? Okay, so that will be something that was something that we already answered using the modular matrices. But today we have another more intuitive way. So I'm going to introduce, for example, fusions and braiding. So the fusion, I want to introduce a notation. You have an anyon A and anyon B. Fuse just use X or the times notations. Fuse A and B, so you can get product, a few different product of anyon. And that could be A, B, C, D, E, etc. And this n here is a non-negative integer. Of course, we only focus on the positive one because 0 meaning that no such anyon is fused into. Okay, so this is the fusion, and we have seen the example above here, fusion. And in our example of Toric, the right-hand side is only one. Only one non-zero. Meaning that you take two of the anyon, you always fuse to another anyon. This is called abelian. So these type of anyon are abelian. If you can fuse more than two, that meaning the right-hand side has more combination than just one, then these are called non-abelian anyons. Okay, this is just a notation and just definition. And we talk about braiding. This case is just exchange. So exchange the two particle. This is the top view, but if you from the side view, you have this this triangle up. You see this. So if you probably do that and this, you will see that as this right hand side. Okay. And you can do it twice. You do the braiding twice, it becomes a rotation. This gives you sort of mutual statistics. So this particle is feeding the statistics field from this particle at the center. Okay. So yeah, so the useful notation that I actually already introduced is this R. This denote a exchange. So A and B represent different type of anyon, possibly different type. And this number can be arbitrary. So unless they are of the same type. Okay, but if you do the exchange or the braiding twice, it return to the original location. So you can ask about sort of self-statistics. You can ask the mutual statistics, how this guy feel the exchange is the statistics from this guy. Okay, so and we have seen this using the, this is S and T matrix. So let's say this is T and this is S. Okay, so maybe it's useful to look at the anyon from the Toric code that we have just learned. So if you exchange the two charges, so even though I draw this, the exchange, but since they are indistinguishable particle, it look as if they were just all move independently and with no additional sign. Similarly for the M particle, okay? But as we see that E and M, if you do a rotation M around E, there's a minus sign. So pictorially, I can view this as 2 of the braiding, okay, and return a minus sign, okay, because E and M return back to its original location. So I can denote that this looks as if the particle travel independently, but with a minus sign there, okay? So if you accept this pictorial way, it's actually quite easy to deduce the fermion property. So how do we see that there's a minus sign when we exchange fermion? And since the fermion are indistinguishable, we can draw a vertical line. But what is this sign here? Okay, to get that, we can use the definition that fermion is a boundset of E and M. So if I exchange the pair, okay, if I exchange this pair, I want to use the rule. So I want to use these rule to deduce what is the effect. So first what I do is I will resolve this here. Resolve, maybe I blow up this part. Okay, so I will resolve this part using this, and this part using the M, and therefore this become a particle E goes by itself, and this become M goes by itself, and there is a braiding. So this part is, yeah, unfortunately, I don't think I can draw at this, but maybe, yeah, I don't think I can draw at the level that blow up. So let me just draw this. I resolve this here. And maybe I try to use a different color to resolve M. Pink color. So this part is to resolve M. Okay, so I'm going to blow this up. So you see that this E goes up, this M goes up, and here there's a braiding, M braid around E, and an E braid around, right? And then we just use this rule that there is a minus sign, and this become a fermion and a fermion. Okay, so using this picture, it's quite useful and give us a pictorial, intuitive understanding of the exchange. Okay, any question so far? Okay, yeah. So there are references for this here. You can go check these. I use the material from some of these papers. Okay. Okay. Let's see. There seem to be people post on charge. E and M here from Toric. Yeah. So I'm using the example from the Toric to illustrate that. Okay, so these are examples on Toric from last lecture, Toric. Okay. Yeah, so given that we know a little about fusion, I want to tell you more. So it is possible that A and B can fuse to various different types of anion. So what we're going to use as a notation is A, B fused to C with a semicolon. And because if the final product of anions are different, if, for example, it's a C or D, they should be different physical state and they should be orthogonal. Right? So we would denote this using also the bracket notation to denote that they're orthogonal because the final product are different anions. This notation is used to denote the fusion space. So A, B fused to C. Okay.
Excuse me?
Yeah.
Is the fusion probabilistic, or do we always get a C, but there is just two possibilities?
So when you talk about this, it's in a sense, you don't always get the same particle if you have different fusion channel, like here. Okay, but you can imagine that it's like a quantum mechanical way.
Okay, so you don't get to determine what.
Yeah, but you have to measure to know which fusion output you get.
Okay, I see.
So are we talking about non-abelian anyons now?
We will be using the most general setup here because I'm assuming that you could fuse to different types of anion. So if we have two different choices or more, then in general, this is non-abelian. But you can also, this reduce to abelian if you can only say D is equal to C, and that's only one, right? Really just one dimensional. Yeah.
Okay, thank you.
Okay, so, but the sort of a drawback is that we cannot use different C as a basis to encode information. Right? So for example, maybe you say, okay, can we use this? And we sum over this and we use some amplitude. Can we do this? This to encode quantum information. So as I said, because C are different anyons, so when you try to look which anion you are in, you will sort of see only one. Right? If you perform measurement, you will only see one. So this can never be used in a coherent way. So it cannot be useful in a coherent way because different anion are the so-called superselection sector. Okay, but this is a jargon. Basically, it means that they are different physical entity. So even though they form some kind of basis, but when you look at it, you can only get one. So you can only get the amplitude square. You will not be able to encode useful quantum information. But we can have more than one anion, sorry, more than two. So for example, we can use 3 anions. And because we're considering non-abelian, so A, B can fuse to E, and then we fuse another C. So basically there are 3 anions to begin with, A, B, and C. And it can be fused, A, B can fuse to E, and then C and E then fuse to D, okay? It could also be that I fuse B and C first, Oh, this is just a mathematical way of seeing what kind of fusion you get. This is like a associativity. You can fuse B to B and C to F, and then A and F fuse to D. Okay, but in each case, I want to fix the final product. Fix final product. If I fix the final product, final fusion product, then I sort of get away from this statement here, because I'm always looking at the final anyon to be the same, but there are different paths. So in some sense, there are different paths to fuse, right? So basically, we're using this as a basis to encode quantum information. So it's like double slit. You sort of go to this or there, as long as you don't look. So no looking here. Right. So if you don't look, then you can use that to encode information. Okay.
I'm sorry, but what is fusion?
Fusion is you take a particle and then you sort of collide together and you see what particle comes out.
So you did nothing.
You put them together, they may be far away. You try to move them closer and closer. And as they sit next to each other, you want to see what comes out. Okay. It's like particle experiment, but not as dramatic. Maybe you get electrons and hit a proton and see what comes out. Okay. But we are not at that.
One
Yeah.
IB will fuse to different particles.
Why it will fuse to different particles? So far, this is just a mathematical model. Okay. So I would tell you what other possibility that comes, what physical system that can get this. Okay. Well, if you want the answer, for example, we talk about quantum Hall system, fractional quantum Hall system. For some of the filling factor, for example, nu equal to 12/5. Actually, this is the subject that I'm going to show next. There are things called Fibonacci annual. But there's only one non-trivial annual, so there's only one. But if fuse two of the Fibonacci annual, they become identity of vacuum plus a Fibonacci. So when you collide the two anyon, it can annihilate to vacuum. It could always annihilate. It could also annihilate to just one anyon left. And this is from possibly from fractional Hall, quantum Hall effect, fractional. Okay. Okay, so maybe I extend your question further. That would show that why we don't have topological quantum computing so far, because it's very difficult to find physical realization of non-abelian annual. Okay. So you can use this as a basis. You could also use 2 as another basis. But they are related by a unitary transformation that's denoted by F. Okay, so this is like associativity, right? Do you multiply B and C first, or you multiply A and B first? So that's very similar. Okay, so yeah, so maybe I want to use a picture. It's easier to visualize. So fusion, I would denote as A and B. They come together physically. If you can move the particle if they are far away, this is what you want. You move them, you really move them next to each other. So they will interact, and then you will wait and see what comes out, okay? So A, B fuse to C, this is our fusion rule. A, B fuse to C, but they are possible, different possible C's, okay? And this is change basis. So here, basically, I fuse a B and C first, that fuse to F, right? And I also have A, Anyon, and then it fuse with F to become a D. So I always want to fix this in my final product. So I use this as a basis, but there's also another basis that I fuse A, B first, and become an E particle. Then I use the E and fuse a C anion to a D particle. And there is a transformation between the two, and this is basis transformation. And fourth, this has to be unitary. Okay. There is also a exchange or braiding that we talk about. Like you just braid the two. You just braid, for example, A and B. So you braid A and B, it become like this. Okay. And if you fix a output of the fusion between A and B, then this would always be a diagonal. So there's this E and this E is the same. So if you write formally, okay, you want to look at the product that A and B is exchanged compared to the one that they are not exchanged. This is intermediate fusion. It's always possible to sum over this intermediate one. However, for these, so just exchange or this braiding, this is just a number that's diagonal. So I'm just indicating that this is Kronecker delta function, meaning that if E equal to F, then it's non-zero. If they're different, it's zero. Okay, so in a sense, when you're doing the exchange braiding here, this E will not change. So it just induces a vector. Okay. So this is the exchange between A and B that fuse a E. But what if I want to exchange? If I want to exchange these pairs of anion, unfortunately, they don't fuse to, in this fusion sequence, they don't fuse to directly fuse together, right? So I cannot do this. I cannot just say it's a vector. But what I can do is I use this basis transformation. So I first do a basis transformation to change into, in this scenario, B and C is then fused to a particle F. Okay. Then I do the exchange. Then I can do the exchange using this rule. It's diagonal. Then I transform the basis back. So it's very similar to what we have seen in the rotation. If we want to rotate around some axis, what we could do is we rotate first to some other axis, do the rotation, and then undo the first rotation back to your original axis. So that's exactly what's doing here. Okay, and you can see, I mean, I'm just drawing this as a picture. I first do the F. So I bring B and C so that they are fused to a particle F. Then I do the R to exchange them, and I do the inverse. Okay, so that's a basis transformation. So, but this effect is that exchanging two particles that are not directly fused according to this sequence, you can relate that to the original exchanged one and in the right basis, in this basis, and it's just some unitary matrix. Okay.
I have a question.
Yes.
Is A fuse B is equal to B fuse A because just the two particle, you just fuse them together? I think they are the same.
Which part are you asking? A fused to E?
A fuse to B and B
B.
fuse to A. If you interchange A and B.
Oh, it's not fused. It's exchange. Right. So you just exchange the two particles.
You said you just remove two particles together, but when you move B to A and A to B, why is that different?
So you're talking about the last part here?
No, I mean A fuse B and B fuse A.
No. So there's no A fuse. Okay. A and B fuse to a particle.
Yeah.
Okay. So this is the fusion, and this is braiding. A and B braid. That means they exchange their location.
Yeah. Oh, okay. I see.
Maybe it's a language issue, but you can see the diagram, right? So the question.
So topology B and this two diagram are the same, right? You just move the line to be straight.
Yeah, but it defines sort of different bases, right? This on the left is B is in the first location, A is in the second location, and as opposed to this one, A is in the first location, B in the second, C is the third location. They can be physically different, and this is related by this exchange or braiding, right?
But if we just look at distribution as the operator, A times B is equal to B times A.
Yeah, so fusion, we don't talk about, yeah, but this is, yeah, you're right. Fusion, we don't care about which one is on the left, which one on the right, because this is just talking about what are the product, right? Just talking about the product. B and A would also fuse to, if you want, so this is A, B, B, A, C, but we basically say that this N matrix is symmetric. Okay, that's for fusion. Okay, but this maybe has additional meaning of the location. A is on the left, B is on the right, which is not emphasized. This is not emphasized here. But here, when we have this, there is a sequence. So A particle is basically here, B particle is basically here, C particle is basically here. Okay, this is different. This can be different. This is different from B, A, and C. Okay. Maybe it's the limitation of notation, or maybe I should not use this, but this is what's used in the literature. Maybe when I do A, B fuse to C, I say A at location 1, B at location 2. But here, when we talk about fusion in this way, we don't specify their location. Does that make sense?
Thanks.
Okay. Yeah, of course, when you use picture, there is some limitation of the picture. When there is problem, you have to refer to the equation. But what I would say here, this fusion is indeed symmetric. You take whether you take A or B, but because if you fuse them in a different way, then that would be a different theory. And that means they don't commute in the fusion. So that would probably depends on how you bring the particle together. Maybe you bring A first and then bring B, and you get different product. Then you bring B first and A. Then that's a different physical situation. Okay. Okay. Of course, these cannot be arbitrary. These F and R, they cannot be arbitrary. There are some consistent equations. I just want to show you that, for example, in this basis change, if you change a different sequence, if you end up the same, so there should be consistency. And this one is called pentagon equation. There's also, if you combine the exchange or the braiding and the basis change, there are different ways to get to the same from the beginning to the end. And this is called a hexagon equation. But don't worry about this. We will not be solving these equations. We will be looking at specific examples that have known solutions. Okay, so maybe it's a good time to look at an example, which is the Fibonacci Anyon that I mentioned earlier. So Fibonacci Anyon is a strange type of anyon, but it's also useful in terms of quantum computation. It only has one non-trivial anyon besides vacuum. So the fusion is that if you take two of these Fibonacci anyon, fuse, it can fuse to vacuum. It can also fuse back to just one Fibonacci anyon. So sometimes you may see in the literature people use a black bar to denote the presence of Fibonacci anyon, and it fuse to identity, fuse to 1. So we use 1 here, but in some other literature you use 0, and this fuse 1, meaning that's 1, maybe 1 tau. Okay, this is our 1. This is our tau. If you want, we could use this to fuse to 1, or tau and tau fuse to 0. The other way around, this would be tau. We would say this is tau. Okay. And you can continue this equation. So usually when we just fuse the two anyon together, the coefficient is either 0 or 1. Right? This is 1 times 1, and 1 times tau. But when you have 3, you take another one, right? So I use I actually fuse these two. I get 1 plus tau from the first equation. I do this fusion again. 1 and tau is tau, and tau is this. But tau and tau can fuse to 1 plus tau, but I have this tau here, so that's why I get 2 tau. Okay. And you can do that, for example, you have 4 Fibonacci anyon fused together. You see that it can only be vacuum or it can only be tau, but you see the coefficient, this particular case is 2 and 3. If you do more, you see that the coefficient from the vacuum become 3, 5. So you may remember the sequence 1, 1, 2, 3, 5, etc. This is the Fibonacci sequence, right? And this coefficient, the coefficient representing number of ways to fuse to this product. Anyon. In this case, it's a vacuum. There are 5 different ways. If you have 6 Fibonacci Anyon, if you have 4, you can fuse. You have 2 ways to fuse vacuum. Okay. Even at the level of 3 Fibonacci Anyon, you have 2 ways to fuse 1 Fibonacci Anyon. So this potentially could be used as a qubit. Okay. Yeah. But the number of qubit does not scale linearly as the number of Fibonacci Anyon. So this is, but the dimension is like a Fibonacci number. Okay, so yeah, so this is what I said. If you use 3 tau, 3 Fibonacci Anyon, if I fix the product to be tau, then this is a possible way to encode a qubit. So meaning that I have 3, right? So I fix the outcome, fix final product, final fusion outcome. And if I fused first 2, it can be fused to 1. It can also be fused to tau, right? And then I consider that it's 1 tau fused to tau, and I consider the second fusion tau and tau fused to tau. I fix that, the final product, okay? But there are 2 intermediate possibilities that I can use to encode a qubit, okay? So it turns out that the R, this exchange matrix, has this form. So it's e to the some pi over phi phase vector. Yeah. So it depends on the conventions. You may see, depending on, you may see my R here could be other people's R dagger. It could be so. Depending on the choice, might be this, maybe R in other convention. Okay. Okay. So next, you can ask, can we get some quantum gate? Since we have a qubit, maybe we can get a quantum gate. How do we do that? Of course, naturally you think, well, you do it from braiding, and that's what is shown here.
Before we start talking about gates, I have a question about the states. So you mentioned that you can have different intermediary channels.
Right.
But how would we encode the qubit into the intermediate channels? What does it mean when you say that?
Okay, so yeah, so maybe we can take a look here. So yeah, so maybe okay, maybe let me just, if you want. Okay, I'll go to this. So for example, you just have 3 anyons, and then you do some braiding that will give you some gate. Okay. So if you can initialize these 3 anyons in a particular state, right, particular configuration, right?
Yes.
Then by doing this, if this is universal, then you can get to any state, any initial state. Okay. So basically, if you have a way to initialize in some fixed state, and if your gate operation is universal, then you can use that, right?
But when you say state, you are talking, the only place where the states differ is in its intermediate part. initial and final are the same.
So for example, I have 3 anyons.
Yes.
Yeah, so what I would do is I would like to measure the final I want to put these, final charge. I want it to be tau.
Yes, yes.
So maybe,
I see it from this
maybe
picture.
it's not possible to do that. You may create from the vacuum but at the end of your experiment, what you would do is probably you would sort of condition on fusing 3 of them into a tau. If you don't get that, then you just throw away that.
Yeah.
Okay. So there might be some post-selections.
Yeah. Yeah.
So you would use measurement to initialize.
Okay.
Yeah.
It's clear from this picture.
Yeah.
I think I understand now.
Okay.
Yeah. Thank you.
So sure. Yeah. Okay. Let's go step by step. So the exchange. We say that if it's fused to a fixed anyon, that's just a phase vector. Okay, and this just says if you fuse 1, 2 tau and tau fuse to 1, under that condition, when you braid them, that's the phase vector you have. So tau and tau fuse. This will be the phase vector e to the 4 pi I over phi, etc. Right? And this is when it's fused to tau, and you braid these to anyon. That's the phase vector you will get. Okay. So I mean, this is solved by some mathematics literature that you have these, and in some sense, this gives us a natural gate. If you can just braid them, these are diagonal gate. This is one of the example of diagonal gate. And we also have basis change, but this doesn't give us any gate in particular. It's just a basis change, right? So, and we have no way to sort of implement this actively. It's just a basis change. Once you fix a convention like this, but this, it's useful to know what the basis change, the transformation is that relay the basis change. And okay, this is solved in literature, but you may see the form could be slightly different. Could be. So literature may use F dagger for that. But the useful thing is when we have 3 anyon and we already fixed the convention to be A fused to B, A fused to E, and C and E fused to D, we mentioned that the direct braiding of B and C is not diagonal, right? So meaning that if I already fixed the 3 anyon, exchanging these two give us the R diagonal gate, right? But then exchanging 2 and 3 would give us a different gate, and which is not diagonal in the original basis. And how you get this gate is related by this formal basis change F. Okay, so that's useful to construct another gate. Maybe I can call it R prime. And with these R and R prime, that's the only 2 operations you can have. You either, so maybe I draw as example in later, you either do this or you do these. Sorry, yeah, you do these. So there are two way you can do, right? And that was the slide that I showed earlier. Let me just skip to that. That's the only 2 operations that I have available. Okay, if I can braid the anyon, these are the only 2 operations. Okay, But there are many combinations, right? You could do this braiding first and then do that, or you do it twice, 3 times, etc. In this particular case, the R is e to the 4 pi I over 5 or minus 3 pi I over 5. So R, if you braid 10 times, is identity, okay? But you can braid 9 times or as many as possible below 10, right? Here you braid 1, 2, 3 times, and then you braid the other combinations, and then you braid this. So this is a sequence of braiding. And if this forms a dense group of SU2, then you have an arbitrary 1 qubit gate, okay? So yeah, so that was the usefulness of Fibonacci Anyon. Indeed, that it's actually dense, okay? But actually, I jump back and forth the slide. So we talk about 1 qubit. We could use three Fibonacci Anyons, right? What about 2 qubit? Well, we could just naively do this, which will be fine. Well, and if you look at this, the fusion channel of the 6, if I say I want the final product, maybe this final product, if I measure and do the experiment, at the end, I need to make sure everything fused to vacuum. Then I only accept that as my computation, okay? If that does not appear to be this case, then I'm picking up the wrong super selection outcome, okay? But the example here is that I fuse 6 anyon. There are 5 possible ways to fuse to 1 anyon. So there is one additional state that I don't need to use. Right? 6 anyon possibly has 5 levels, 5 different choice. So this is more than 2 qubits. Yeah, slightly more than 2. And it could also be useful in a way that maybe this additional space that allow me to do some gates, which would not be possible if I only have strictly 4. Okay, yeah, so there was one question on where do we get this kind of fusion that you fuse 2 Fibonacci anyon and you don't always get the same outcome. You get 2 possibilities. It's either vacuum or it's either the Fibonacci anyon itself. One possible place is this nu equal to 12 over 5 in this fractional quantum Hall effect. I think it's in this location. So 12, it's 2.4. So this is feeding factor 2, feeding factor 3. It's very difficult an experiment to get this version. Right? So for some other corner Hall plateau, it has a wider plateau, but for example, this has a really wide plateau. It's quite messy here, and so it's probably not yet confirmed that we have even this nu equal to 12 over 5 being a Fibonacci anyon. So I don't think there's any experimental confirmation. Okay, but this is probably the most ideal place that you have quantum computation to be very useful. Okay, so I mentioned the 1 qubit gate. You could also do the 2 qubit gate. And you take 3 anyon as a group, and you have 2 groups of them, so you have 2 qubit. There's some work I quoted here, that if you braid sort of these 2 anyon with other anyon, and the braiding is quite complicated, this could be used to approximate a CNOT gate. Okay, I think the way that they found this is that they just use the computer program to find a search, to search this braiding, the sequence. Okay, so combining this is SU2 dense plus C naught, then it's universal. Okay, universal in a sense, you need to have many groups of them. Right? You need to have your quantum circuit, right? Like this. You need to have as many as possible. But the element that you use to decompose into gate will be using these braiding sequences. Okay. It's quite pictorial, intuitive, but to find the number, you need to do some search, numerical search for that. Okay. But that's the most ideal place for topological quantum computation.
The paper leg on your iPad. The paper leg ships with 2 paper leg screen protectors, 2 dust absorber guide sticker sets, 2 help stickers, 2 oversized.
Your mic is open.
Yeah, because somebody.
One other thing we ship is a postcard made by
This mic is
I probably have to.
I probably
have to maybe mute.
One thing we don't ship is a card.
I'll mute everybody. Okay. Yeah, maybe there's a parallel lecture going on. Okay. So, but we don't have this ideal Fibonacci Anyon yet. So the next bad thing that we might potentially have is this Ising Anyon. We're running out of time for today, but this is related to the Majorana fermion that I talk about, but that's just introduce its fusion. So there are 3 anyons in this Ising Anyon model. Vacuum, this is called fermion, and this is the Ising Anyon. It's a particular Ising Anyon. And this is the one that corresponding to the Majorana 0 mode that bound to a vortex that we mentioned earlier. The fusion is, of course, for a vacuum. If fused with any anyon, it's always that anyon. And if you have 2 fermion, it will fuse to a vacuum. Maybe if you have a fermion fused with the Ising anyon, it becomes the anyon itself, sigma anyon. If you fuse 2 sigma, it can become vacuum, and it could also become a fermion. So a useful physical interpretation is that if you imagine a condensate Cooper pair, they are Cooper pair of electrons. One is the condensate, the sort of the superconducting state. Psi is the Bogoliubov fermion. You sort of break this apart. You have electrons, and sigma is the Majorana bound state. And we know that if you have 2 of them, you could have no fermion. You could also have 1 fermion, right? So because, for example, this gamma is C1 plus I, C2. So the gamma is half of the usual fermion. If you have 2 of them, you can have a 1 fermion, but it's a mode that you could not occupy or you could occupy. So that's why you have 2 fusion outcome. And what about this one? This one is basically, if you put a fermion on that, it can occupy that mode. So it still is a Majorana fermion or a Ising anyon. Okay, so that's the physical interpretation. Okay, so then we can look at if we want to fuse more than 2. For example, if you fuse 3, I already fused the first 2, and I fuse that with the 3rd anyon, and it becomes 1 sigma from here, and psi fuse with sigma is another sigma, so you have two sigma. So that 2 means the 2 ways to fuse that. So in our notation, we fix the final product. We fix this final product. Oh, I think it's quite terrible. Today I forgot. Did I record?
You're recording right now. So.
Okay. Okay, good. I forgot. I thought I forgot to press the recording. Okay. So back to this. So we fix the final output, and fusing this, if you fuse the first 2, it could fuse to vacuum. It could also fuse to a fermion. So these are 2 possibilities that you get to the final product, and you use this as a qubit basis. Yeah, so perhaps we will stop here and we come back with Ising Anyon. Yeah, we already are over our time. Any questions?
So I suppose sorry, just
go ahead.
I suppose the benefit of Ising Anyon is we don't have any fail probability in this sense, right? Because everything is.
But here you still need for example, this final output is sigma, right? You still have different ways. So I think the benefit of Ising Anyon is potentially we are almost there. So let me just go to the. We talk about physical system. Let me just skip this. This will be the topic. So we have a few physical system to realize this, and experimental results show that they are consistent with the Majorana fermion at the end, but so far there's no braiding. There's no experimental measurement on the braiding. So if we can do the braiding and confirm that this is an Ising Anyon, then that can be used for quantum computation. So that's the next thing that we could have. The drawback is that it's not universal. The natural gate from braiding is not universal. So we need to do something else, right? So either you have perfect scenario, which is really hard to realize physically, or you have the sort of the next things, but it also have other disadvantage. And so you see that it's really not easy to construct topologically protected quantum computation. Okay, so that's the reason.
Thank you.
Okay, sure. Maybe I'll stop recording. And I want to remind you again to work on your midterm report. This is mostly for yourself to check how you're doing. And then that would also let me know how you're doing and how I would adapt to the subsequent lecture. Okay, we'll stop here and see you next week.